Hello, this is Lorraine Jamison, and this is GoReact, the final exam. Hopefully this will be under 15 minutes, but if not, this will have to be split up into two videos. So here we go. Number one, show that the equation is homogeneous and solve with substitution. So in order to prove that this is homogeneous, it needs to be to the same degree. So mtx_ty has to equal ntx_ty. So in order to do this, you just each multiple variable should receive a t, so the t is distributed and then factored out. So this equation is homogeneous to the degree 2, and then it's the same on this side, so negative t squared x squared factors to t squared times negative x squared, so that means it is also homogeneous to the degree 2. So we were supposed to solve this using substitution. So here are my substitutions. Y equals ux, and thus dy is equal to x du plus u dx. So basically what you do is you replace the y and the dy in the equation, with these two substitutions. So when you do that, you get u squared x squared plus ux squared dx minus x squared u dx plus x du. And so from here, my goal was to simplify and separate the dx's from the du's. So I did just that, and you get the simplified equation right here. X squared u squared dx is equal to x cubed du. And then divided both sides by x cubed du squared. And then I integrated both sides to get ln x is equal to negative 1 over u plus c. And knowing what y was, I could solve for u also, so u is equal to y over x. So ln x plus 1 over u is equal to c, and then you just use this substitution back down in here. Ln x plus 1 over y over x equals c, and that simplifies to x over y. So your final equation is ln x plus x over y is equal to c. Problem 2 was to solve the equation via variation of parameters. And so we have y double prime plus 3y prime plus 2y is equal to sine e to the x. So first we have to find the complementary solution, which you do by substituting m squared in for y double prime, 3m for y prime, or 3y prime, and then 2 for 2y. And you set this equal to 0 to solve for the homogeneous case first. So you have m plus 1 times m plus 2 is what this factors out to. So m is equal to negative 1 and negative 2. So your yc is equal to c1 e to the negative x plus c2 e to the negative 2x. So after we've found the complementary solution, we are then able to find the Wronskian. And so what this is y1 and then y1 prime, y2 and y2 prime. So you take the determinant of this to find the Wronskian. So it's right there. W1 is equal to 0 f of x, y2, y2 prime, y prime 2, whatever. So you once again take the determinant, and that is equal to negative e to the negative 2x times sine e to the x. And then Wronskian 2 is y1, y1 prime, 0, and then f of x here. And then you once again take the Wronskian to get this. Now, your y particular is in the form of u1, y1 plus u2, y2. And you know that u prime of 1 is equal to w1 over w, and then u2 prime is equal to w2 over w. So in order to solve for u1 and u2, I took that division problem and then I integrated. So on both sides, the integration was a little bit complicated, but this integration was just an integration by substitution. And then this one was an integration by substitution and then an integration by parts. So u1 was equal to negative cosine e to the x, u2 is equal to e to the x cosine e to the x minus sine e to the x. So like I said, the y particular is in the form of u1 y1 plus u2 y2. So then the y particular is equal to negative cosine e to the x times y1, which is e to the negative x, plus e to the x cosine e to the x minus sine e to the x. times e to the negative 2x, because that is y2. And then y is equal to the particular plus the complement. So y is equal to c1 e to the negative x plus c2 e to the negative 2x minus cosine e to the x times e to the negative x plus e to the x cosine e to the x minus sine e to the x, all times e to the negative 2x. The third problem was to use the Laplace transform to solve the IVP. And so the problem was y double prime minus 2y prime plus y is equal to e to the t, and y of 0 is equal to 0, y prime at 0 is equal to 5. So in order to do this, because the Laplace is a linear thing, and this is a linear equation, you can distribute the Laplace to every term in this equation. So the Laplacian of e to the t is just 1 over s. That was super simple. And then these Laplacians are equal to, so the Laplacian of y double prime is equal to s squared y minus s times the quantity of y at 0 minus y prime at 0. And then minus 2 of the Laplacian of y prime, which is minus 2 times s capital Y minus y at 0. And then plus y, which is just y. And then that's all equal to this left-hand side. So basically all you have to do here is to simplify and isolate the capital Y. So then the y times s squared minus 2s plus 1 is equal to 1 plus 5s over s. So y is equal to 1 plus 5s over s times s minus 1 quantity squared. And then in order to solve this, you use partial fraction decomposition. So in this case, I got a equal to 1, b equal to negative 1, and c equal to 6. And then there's just all that work. And so you can replace those in a, b, c. So the inverse Laplacian of y is equal to 1 over s minus 1 over s minus 1 plus 6 over s minus 1 squared. And so this was quite an easy inverse Laplacian today because 1 over s is just 1. 1 over s minus 1 is e to the t. And then 6 over s minus 1 squared is 6t e to the t. And then oh, I did not open the last one, but we will open the last one here. Do, do, do. Cool. So here's the last one, was to find two linearly independent power series solutions. And once again, I was not 100% confident on how to do this or what the answer was, so I will just show you my work that I did and hopefully get some partial credit. So this is x minus 1 y double prime plus y prime is equal to 0. So I just distributed the x minus 1, so it's x y double prime minus y double prime plus y prime is equal to 0. And so y double prime is equal to the sum n equals 2 of cn n times n minus 1 times the quantity of x to the power of n minus 2. And then y prime is equal to the sum at n equals 1 cn times n x to the n minus 1, and then this is obviously just like the same thing except subtracted. So I distributed the x into the equation, and then you have to get the x's to the same multiplicity at the beginning. So what I did was I found x of 1 here and x of 1 here, and in order to do that, you just take and find, so n has to equal 3 here and n has to equal 2 here, so you plug in n equals 2 here and you just add it onto the front. And same with this case, n equals 1, so you have to get this to n equals 2. So you find the value at n equals 1, and then your indice will start at 2. And after that, I wanted each, after I found the same indices, I wanted each to, or the same x powers. You have to make the indices equal so that you can combine the entire power series. And so I got C1 minus 2C2 plus the summation at n equals 1 of C n plus 1 times the quantity of n plus 1 times n minus C n plus 2 times the quantity of n plus 1 squared plus C n plus 1 times the quantity of n plus 1 all times x to the n is equal to 0. So in order for this to be true, C1 minus 2C2 has to equal 0. So C1 equals 2C2, and then C2 is equal to C1 over 2. And then C1, so this inside part also has to sum to 0 for this to be true. So I set it equal to 0 and just did some algebra here. So Cn n plus 1 times n plus Cn plus 1 n plus 1 is equal to Cn plus 2 times n plus 1, and then I simplify it. So you get n equal, sorry, so you get Cn plus 1 is equal to Cn plus 2, so C2 is equal to C3, C4 is equal to C5. So that means that a constant is true here, so y1 is equal to C naught, and then y2 is equal to the summation of n equals 1 over n times x to the n, because after that you just substitute it in at the y equals C1 plus C2x plus C3, blah, blah, blah. So yeah. Before I go, I just want to thank you for such a great summer semester. This is the first time I've taken a summer course before, and it was actually quite fun. It helped me to stay like focused and active during summer. And then I just want to thank you because your lecture videos were so much better than my previous math prof at UIUC. And I think it was super helpful that you included a lot of examples and that you walked through a lot of examples quite slowly. And at least for me, that just helped me out a lot to see where some of the work was going. And it also helped me, like, as I was reviewing, to be better prepared for the final exam. So thank you for a great summer semester, and I wish you luck on the next fall semester and any other coming semesters. Thank you.